Ladies and gentlemen, my presentation is related to so-called the principle of structural design. That is the way in which we organize our design. First of all, we have to consider the design situations. And in these design situations, we have to account for direct actions, indirect actions, and environmental actions at the same level. So actions will be compared in the analysis and the verification with structural properties, and we have to consider that generally both may be variable in time and during the surface life of the structure. Then, having this set of actions and properties, we have to select the design situation, and the design situation should be considered in relation to a time interval. We will consider in design situation load cases, which is the most common in the design, the hazards related to the robustness, and in general the limit state that should be checked. Those design situations are the foreseeable conditions which we have to expect during the execution and during the service life of the structure. We can distinguish four types of design situations. Persistent situations are referred to the normal use of the structure during its service life. The reference period TR for them corresponds to the service life. That means that for new structures, generally we adopt 50 years for buildings and 100 years for bridges. Also more for special structures, generally nuclear plants or Messina Strait crossing, which will not be built but was designed 200 years. For the existing structures, they may coincide with the residual service life. The transient situations are referred to temporary conditions of the structure in terms of use or of exposure, and the reference period is generally 1 year. Accidental situation corresponds to the exceptional condition of the structure or its exposure, like the fire, the explosions, impacts, terrorist attacks also, and are actions of short duration, unlikely to occur, we hope, during the service life, but potentially able to produce catastrophic consequences. In this case, the reference period TR is equal to the event duration. Then we have the seismic situation, which are referred to the structural conditions when subject to an earthquake, and the reference period TR is equal to the surface life or the design for the new structure or residual for the existing structures. Well, we have to use design strategies against these design situations. The design strategies that we apply in persistent and transient situations may be design the structure to sustain the action, is the most current case. Design the structure to avoid the action, protect by means fenders, for instance. Design the structures to limit the damage. In case of accidental seismic design situation, again, we can design the structure to sustain the action, very expensive sometimes. Design the structure to avoid the action, or design the structure for a sufficient robustness. We have to consider, in this case, explicitly the robustness. What are the design methods? We have a specified set of limited states which distinguish the desired states from adverse states that we consider general in the design. We define a limit state function, G, which is function of actions and resistance. E, the actions are the resistance. When G is 0, we have attained the limit state. The failure then, or adverse state, is characterized by a value of G smaller than 0. If we assume that R and E are independent, it's not true in any case, but we can modify R and E to render independent. The previous expression may be written in a different way, separating the variables related to the resistance from that one related to the actions. And then we can write that R minus E equal to 0 is the limit state, the reachment of limit state. Then the failure or the adverse state becomes R not greater than E. If we define limit state, we need safety formats for the verification of the limit state. And the basis of all the safety format that we use is probability based. But we have different possible approaches for the safety format. A completely probabilistic safety format for special cases, partial factor safety format to be used every day. Global resistance format is relatively new, again for particular cases. Deemed to satisfy approach we use currently in the design, designed by avoidance when we do this choice. The probabilistic safety format implies the verification of reliability requirements in terms of reliability index beta and reference period. Is seldom used for the design of new structures because we have to recognize that we have lack of statistical information necessary to perform completely this, in a correct way, this safety format. But sometimes it's used with some assumption. It's more used, in my opinion, for the assessment of existing structures, but of course, due to the weight of this operation, when is economically justified. Partial factor safety formats correspond to a verification of reliability requirements by means of a set of gamma factors which has been calibrated to give a sufficient safety margin during the service life that is calibrated a priori by the code writer by means of the probabilistic format. Global resistor format, with this approach as implicit in the name, the resistance is considered at a global structural level, not locally section by section, but regards the global behavior of the structure. It is especially suitable for design based on nonlinear analysis by means of numerical simulations. Deemed to satisfy approach includes a set of appropriate values from a set of predetermined alternatives given in a standard. It's used generally for the verification of service-life design new structures. For instance, we have tables in which we design the cover, taking into account the exposure class, type of cement, and so on. This is a deemed to satisfy approach. Design by avoidance is based on the avoidance of the actions, is applicable both for traditional design and for service-life design. For instance, I use, in case of corrosion by chlorides with high level of exposure, I use stainless steel in the external layer of reinforcement. For each limit state verification, we have to identify the basic variables. The variables are the actions, the environmental influences, the material and eventually the soil properties, and the geometrical parameters. For a probabilistic safety format, the basic variable may be described by means of random variables in new structures when we assume that within the same structural element we have the same distribution of resistance, or also with random fields. For instance, for the evaluation of damage, deterioration in time of the structure, which intervenes in a non-homogeneous way along the structure, then we can define different probability density function for different regions of the structures. For instance, in a column, in a square column, the reinforcement which stays in a corner receive aggression by two sides. And its position is different from the reinforcement which stays in the middle of the face, which is receive the aggression just from one direction. In case of partial format the basic variable, partial factors format, the basic variables are deterministic quantities because we are covered in the design by the gamma factor. And for global safety format, generally the global resistance of the structure is considered as a random variable. To verify the attainment of the limit state, we need a model. Then for each limit state, we should establish models which are able to describe the structural behavior. Those models may be mechanical models or physical or chemical models. It depends by the type of limit state that we are considering. The parameters of the models should be treated as basic variables. And we have to include in this treatment the evaluation of model uncertainties. Our models are not perfect. You know that nature is not deterministic. It's not probabilistic, it's not random, following some interpretation is unfocused. But also, if it was deterministic, our knowledge of the nature is not perfect, then we need to introduce model uncertainties. The models may be analytical or numerical, but any case should be supported by testing. Do not accept models invented by someone with a brilliant theory to demonstrate something if you have no experimental test. Well, now we enter in the detail of the different safety format. With the probabilistic safety format, we have the need to estimate the probability of failure, or, which is equivalent, the reliability index, beta. We said already that it's suitable in general for assessment of existing structures. We use this system when we have doubts about the performance of a structure. An existing structure may show a behavior which is outside the range of we expect in terms of deformations, vibrations, and so on. Opening of the cracks, for instance, what we see immediately. Or at the expiration of design or residual surface life. You can imagine that we have a structure of 30 years, we give further 20 years, but when we finish the second 20 years, we cannot restart with other 20 years. We need a global, more refined verification of the structure. Or to detect the effect of design or construction errors. Sometimes at the end of the construction, you discover that there are errors in design or in construction. Then to evaluate what is the actual effect of these errors, you need a refined method. Or in occurrence of unusual incidents during the use. After an explosion, the structure is damaged, the evaluation of residual bearing capacity and the possibility to intervene to repair instead of a demolition may be evaluated with care and then by use of such type of format. Or when is planned a change of use of structure, which is revolutionary. Not, of course, if I say this is building, remain buildings for the people, but the live load is 200 kilos per square meter instead of 150. It's not the case. But if I change completely destination, I need a more refined verification. It's suitable of support to design with partial factors, because it's the basis for the definition of partial factors, or deemed to satisfy approach to ensure an adequate robustness to the structure, or to account requirements which are out of the range of the scope of the Model Code 2010. For instance, actions and hazards not covered in the Model Code. What I have to do? I use this nonlinear analysis and the probabilistic approach. Use of materials or their combination outside the usual range of experience. If I use composite, timber, and concrete, I'm not covered by the codes, but it's possible to use. Then I need a more refined approach. Service requirements outside the range of covered by the Model Code, 200 years, for instance. Reliability level not covered by the Model Code. Unusual structural system or systems or geometry. The fantasy of Howard that you know is very large. In particular, for what I call, I collaborated with several of them, the ArcStar. Or very high consequences of failure. In this case, a structure which shows a trend to have very high consequence of failure should be investigated with a proper safety format. The basic rules for the probabilistic approach consist in the evaluation of a probability of failure, PF. That is the probability that the function G or limit state is smaller than 0, or a probability that the safety margin M is smaller than 0. If we separate the variables, alternatively, we can say that probability PF is the probability that R is more or equal to E, and is the probability that R is small, R of R, and then R directly is smaller or minor of E. In this case, we call the attention that because we perform the integration on the Q's of the distribution of PDF, a proper choice of basic random variables, PDF, is very important because the result of reliability analysis are very sensitive to the type of distribution chosen. You attain different results if you use Gaussian or log normal or Weibull distribution. Then you have to be sure that the PDF that you are using is correct for the action or the resistance that you are considering. Partial factor format. Here we have a separation of a treatment of uncertainties and variables by means of the use of design values that we assign to the variables. This separation in general terms is not correct because we said already that sometimes various factors are not mutually independent. For instance, in a continuous beam, actions and resistance are not independent because if I have a variation of parameters of concrete in one span, the distribution of internal action is different. In particular, should not be used with the closed days that you use but thinking on the result, when nonlinear limit state equations describe the verification, when the variables are mutually correlated, and absolutely not in the design by testing. The basic variables with this safety format are the actions, the material and product properties, X, and some geometrical quantities that generally are covered by tolerances. And then, again, the model uncertainties, theta. The design condition is a function of describing the limit state, G, which is a function of design actions, FD, design resistance, XD, geometrical parameters, AD, model uncertainties, theta D, and serviceability constraints should be greater than 0. Alternatively, you can separate actions and resistance, as we said. The design condition has a large freedom, can be formulated in the space of internal and external actions. Generally, we compare acting or resisting bending moment in a beam. In the field of forces, when we refer to the overall structures, it's more suitable to compare the ultimate actions with the ultimate resistance of the structures. In terms of stresses in the verification of fatigue, I check that the sigma, the delta sigma in case of fatigue, is smaller than alpha times the resistance. Or of geometrical quantities, and may be used also for the seismic actions if we consider as a parameter for the satisfaction of verification the PGA, the peak ground acceleration. The actions, design actions, are evaluated by application of partial safety factor gamma F to the representative value of the actions. The material or product properties, FD, are design values, are obtained by the characteristic 1 divided by gamma M, M capital, or by a product of gamma M smaller by gamma D. In this case, we separate in the safety coefficient the model uncertainties. Then we can treat all together in gamma M capital, or we can separate gamma M smaller related to the randomness of the variable, and gamma D are the model uncertainties. We already commented this one. The geometrical quantities, AD, design values, are the characteristic value plus the tolerances. And the model uncertainties, gamma D, or 1 divided by gamma D, it depends if they are applied to the actions or to the resistance. For existing structures, the design values of basic variables may be reconsidered. I think it was a question of yesterday afternoon to Professor Walraven. And we have some indication in ISO 13822. The normal random value, if we use a Gaussian, is XD equal to the mean value by 1 minus alpha beta V. Alpha is the sensitivity factor of the form. We will see in a moment its value. Beta is the target relativity index, which for existing structures may be updated, may be reduced, and substantially reduced. In my keynote of Monday, I showed that we can arrive from 3.8, starting from 3.8, also to 2.5 for the buildings. That means for the bridges, we may arrive to 3.3, 3.4. 3.3 is in discussion in this moment in Europe. V is the updated coefficient of variation, not what we assume for the new structures, for instance, 15% for concrete. No, I test this structure, I update the value. And sigma power 2 is the logarithm of 1 of V power 2. This appears in the second expression, which is related to the log normal random value when we use log normal expression like we use for the resistance description, because the limit is 0. Negative resistance has no sense. In this case, the design value of the resistance of the variable is xt, is the mean by xp to minus alpha beta sigma, and generally we stop here, because generally we have a coefficient of variation smaller than 25%. If it is not this case, we have to add the second term, which is 0.5 square sigma power 2, and then this because this term cannot be disregarded in cases in which the coefficient of variation is so large, but is generally not our case. The alpha coefficient, like for the new structures, assume the values minus 0.7 when the dominating parameter is on the action side. This is a correction factor because we use the form. Form is the first order reliability method which introduced some simplification in the definition and the control of the limit state function, because it linearize the limit state function. 0.8 for dominating parameter at the resistance side, 0.3 by minus 0.7 for non-dominating parameter at the action side, and 0.3 by 0.8 for non-dominating parameter at the resistance side. Alternatively, we can calculate the rate characteristic value, and the design value may be derived by the characteristic one by application of gamma m. That is, we evaluate xk, characteristic value, which is a probability chosen a priori to be not overpassed in the TR, in the duration life of the structure, which for random variables is the mean minus 1 k times the coefficient of variation. For log normal is the mean by x to minus k sigma plus the second term when it is necessary. And k is 1.64, which corresponds to 95 or 5% fractal, depends if we are referring to actions or resistances. Actions with partial factor method, we said that we need representative values of basic variables. The actions may be direct or indirect, that is forces or imposed deformations. We have to distinguish between permanent, variable, and accidental actions, static, quasi-static, or dynamic, closely bounded or not closely bounded, fixed or free. For instance, if we refer to permanent actions, we may use a single value of G. G is the symbol for permanent action. G is gravity. And we will use, in this case, the mean value if the variability in time is small. The weight of a structure is generally very low variability. If the influence of this action on total effect is small, or one of two representative values governs all along the structure. That is, in case I use two representative values, superior and inferior, if G superior governs all along the structure, I may use the mean value. Otherwise, I have to use two values, the favorable and unfavorable, G-sup and G-inf, which are the fractal 95% and 5% of the distribution of G. Then G-sup will be 1.1 GM, G-inf 0.9 GM. Those coefficients are reduced to 1.05 or 0.95 for the construction of cantilever bridges, for instance, in which the quality control is greater than in a building. And in general, we will use these two values in one particular verification, the static equilibrium. We will attribute 1.1 to the unfavorable effect of 0.9 to the favorable effect of the weight. Then we have to use the combination values of different variable actions. We have a characteristic value QK, determined as we said before, a combination value which is QK by psi0. Psi0 takes into account the reduced probability of simultaneous intervention of most unfavorable values of several independent actions. Then if I have three different variable actions, the probability, which are actually independent, the probability that at the same time I have the characteristic value is smaller than 1, and then I use psi0. Psi1 is a coefficient which corresponds to the frequent value of the actions, that is the value that is exceeded in 5% of lifetime of the structure. Psi2 represents the values that is exceeded in 50% of the lifetime and correspond to the quasi-permanent combination value of the action, Psi2. You see in the table the values that are assigned for buildings with different destinations to this variable. For instance, if we take one EV category, category E, storage areas, psi0 is 1, because if I have a storage area, I will fill. Psi1 is 0.9, psi2 is 0.8, because I suppose that I will use the storage area. But for domestic residential category A, psi0 is 0.7, psi1 is 0.5, psi2 is 0.3. We have reduced values. Now we have the accidental actions AD. We have to define representative values of these actions, and this is not easy, but we will refer to the scenario that we consider for the robustness. Representative values generally AD is also a question of agreement with the owners. Representative values of seismic actions are values defined with a prescribed probability of not being exceeded during the service life of the structure, TR. And we distinguish 4 limit states: the operational, the immediate use, the life safety, and the near collapse. The operational limit state corresponds to the frequent seismic action expected or to be expected at least once in TR. Expected then to be exceeded in TR once. Immediate use limit state is occasional earthquake not expected to be exceeded in TR. Life safety limit state is the value that we use generally for the seismic design, is a rare seismic actions with a probability of 10% to be exceeded in TR. Generally we use this one, which for the buildings corresponds to a a period of return of the seismic action of 475 years. Near collapse limit state is a very rare seismic action with a probability of 2% or in the range 2-5% maximum to be exceeded in TR. For instance, when you design a bridge with isolators, you are obliged to verify both this ultimate limit state. You design for life safety, but you have to check that the excursion of isolators and joints is able also to reach the level of near collapse without modifying the statistical scheme of the structure. How we define the seismic action? With an elastic response spectrum, which is modified then in design spectrum, for a single degree of freedom oscillator with 5% of a critical damping, considering, of course, the subsoil conditions. Then the elastic is soil dependent, the elastic spectrum. Or with time histories of relevant components of ground motion, generally defined with 3 components of ground motion. And for these time histories, we may use historic records, if enough. We may use simulated records starting from the geoseismical characterization of the soil, or very often, most often, artificial records, numerical generated, and based, controlled with the spectrum calibrated with the elastic spectrum of response. In other actions, in general, process is an action. Then we have to represent the process as action. In particular, the losses. The losses are assumed that with their mean value, delta PM, which is a function of the coordinate, the position of the point respect to the anchorage. In the anchorage, I have x equal to 0, and the time. Then, when I refer to time 0, I'm talking about the mutual effect or of a different tensioning or the friction, for instance. But time means relaxation, shrinkage, and creep effect on the losses. And are evaluated under the quasi-permanent combination of actions, conventionally. Then, the PM of xt is P in 0, 0, that is at the anchorage at time 0, minus delta PM of x in the position, the section which are considering at time t. Pay attention that if the length and the angular deviation of tendons are not exceptional, that is delta PM of xt divided by P00 is smaller than 0.3, then less than 30%, approximated values for pk sub and pk inf can be used. Properties of materials. The strength of material properties, we said, are considered as basic variables. Then we have characteristic strength, Fk, or in general xk, general properties, if it's not a strength, or mean values, Fm or Xm. The geometrical quantities are introduced in the process with a nominal value, that is the value that we attribute in the design. A beam with a width of 30 centimeters, 30 is the nominal value, plus the tolerances, unintentional eccentricities, unintentional inclinations in buildings, curvatures, depth of reinforcement in members thinner than 100 millimeters should be taken into account as basic variables. Generally, unintentional eccentricity, inclination, and curvatures are given in the codes. You have to consider some eccentricity in the analysis. Pay attention, then when you have a concrete member very thin, less than 100 millimeters, the A nominal plus tolerance may not cover completely the safety aspect. Then in this case, it is better to describe the effect of geometrical error in positional reinforcement as a basic variable. In this table, you have the tolerances. I will not enter into detail, which are accepted for slabs, for columns, and also on the positioning of order reinforcement or precessive reinforcement. Then values that should be checked are not that one that you will use in practice. Those are the values that you assume in design. In practice, you will have the codes on the execution, which of course are more restrictive. That is, if I accept 15 millimeters on one parameter, when I consider the corresponding parameters in the code on the execution, I will find 12 or 13. Are more prudent in assuming these values in the analysis. Here you have the tolerances on covers for different type of structures. Well, what are the basic rules that we use for the definition of gamma factors? The gamma factors that you see inside the model code are intended for the new structures. For the existing structures may be reduced in agreement with the beta reduction. I try to accelerate a little bit. In the ultimate limit state, generally we have to control that a generic strain is smaller than the limit strain for the material. But for operational simplicity, we do not perform this verification. We perform the check in terms of internal actions, ED, and the resistance, or internal actions in case there is just one component that is bending moment, resisting bending moment acting, or when we have a multi-component internal actions, I compare the internal action with safety domain, an interaction domain 2 on 3D. The variables that should be differentiated on the action sides are the self-weight, other permanent actions, variable actions, pre-stressing, and others like earthquake, fire, accidental actions. On the resistance side, concrete strength, steel strengths, and modular uncertainties. For the materials, gamma M, we said is the product of gamma M smaller by gamma RD. And gamma RD, the coefficient of model uncertainties, is the product of two model uncertainties. One is the actual model uncertainties, and the other is a partial factor for geometrical uncertainties. Generally, gamma RD1 is 1.05 for concrete strength, 1.025 for steel strength. Gamma RD2 is 1.05 for the size of contract section or reinforcement position. This assumes the same value. For concrete, then gamma RD becomes gamma RDC. We have 1.05 by 1.05, that is model uncertainties is 1.1. For steel, 1.05 by 1.025, model uncertainty coefficient is 1.08. Then, if we have a Gaussian distribution, gamma M is the ratio, gamma M smaller, between characteristic and design values. That is the mean value by 1 minus k times the coefficient of variation, divided the mean by 1 minus alpha beta delta R, and I can simplify, we can reduce mu R. For log normal, we have a similar expression, and if we consider that k is 1.64 and alpha R is 0.8, beta 3.8 for buildings, and the consequence class 2, that is normal effects of collapse of failure. Delta R are assumed for the definition of a coefficient we have in the code as 0.15 for concrete, 0.05 for steel. That means that applying those numbers inside the previous expressions here inside here and here, we arrive for concrete to 1.1, which was model uncertainties, by 1.39 to 1.52, we use 1.50. And for steel, we have 1.08, which derives by the application of a coefficient of delta S of 5%, by 1.08 model uncertainties, 1.17, and we use 1.15. This is the origin of our safety coefficient. For the permanent actions, again, we can introduce a partial factor for the model uncertainties. And then we have a partial factor for action variability, gamma G small, by gamma SD. Gamma SD is 1.05. That means that the gamma G sup with alpha E to minus 0.7 and beta 3.8 is depending, as you see in this expression, by alpha E, which is fixed, by beta in the first line, beta 3.8 is fixed, then by delta G. If we assume 1.05, we have to distinguish between self-weight of the structure and other permanent actions. If we do not perform this distinction, which is convenient, we use 1.10. Then with delta 1.05, gamma G sup is 1.13 with the previous expression at the top of the page. And with 0.10 is 1.27. The consequence is that gamma G capital is 1.13 by 1.05, that is 1.19. Then if we separate the dead weight from the other permanent actions, the gamma G is 1.2 and may be convenient in several conditions, for instance in bridges. In the other case, we have a 1.27 when we consider together, by 1.05, 1.33, and we assume in the code 1.35. For gamma F, we have these common values. For the permanent actions, gamma G sup between 1.05 and 1.10, we already commented. Gamma G inf 0.9, 0.95. For the pre-stress in general, we use 1. In case there are external tendons and we have to expect important second-order effects because the deviator assumes a large distance in these tendons, gamma P is 1.35. For local effects in the deviators, 1.2 on the anchorages. For the leading variable Q, 1.5 or 0 if is favorable. And for accompanying variable actions, 1.5 psi 0 I, depends by the verification, or 0. Those are for persistent and transient situation in verification of static equilibrium. Then we have a persistent and transient situation for verification of structure. Geotechnical actions are not involved in the verification. Then for the permanent actions, we said treating together the two, the load and other permanent actions, gamma G 1.35 or the favorable 1, pre-stress 1, and for the variable actions, 1.50 or 1.5 psi 0I 0. Alternatively, take into account that concrete structures are massive. We may use part of the safety implicit in the dead weight respect to other materials, respect to these steel structures, in the verification. That is, alternatively to the previous one, we have two sets of coefficients, and we have to use the most EV combination. That is, in the first one, we may use 1.35 for gamma G or 1, the precess is 1, but also the leading variable is affected by coefficient psi0, 1. Then I reduce the leading variable. Otherwise, I can use a reduced dead weight that is 0.15 coefficient. That is, I reduce by 15% the gamma G and remain with the other coefficient. The most onerous of this combination should be used. For accidental seismic situation, gamma F is 1 for all the actions. For materials, concrete, we have a gamma G equal to gamma C equal to 1 because we evaluated before. For tensile strength, you have to check all the design clauses. For accidental combination, gamma C is reduced to 1.2 and tensile strength C design clauses. For the reinforcement, gamma S is tension compression 1.15 as we evaluated before, 1 in accidental combination. Well, you know these combination formulas. The difference between these two formulas is that the first one includes the treatment of model uncertainties inside the gamma coefficient, which have the capital letter gamma G, gamma P, etc. In the second one, the gamma G do not include the model uncertainties, and then we multiply the evaluation, the effect evaluated by means of gamma SD related to the model uncertainties, the linearization procedure that should be used when ED is an underproportional function of actions for safety side, on the safety side it should be used, or the effects or some actions oppose to each other with the same order of magnitude. For instance, the pre-stressing and other actions, permanent actions, a part of a live load has the same effect with the same opposite effect with the same order of magnitude. It is better to use the linearization procedure. The fundamental combination then includes the possibility to have a gamma G sup and inferior. In the accidental combination, I call the attention that gamma is equal to 1. The accidental action is described by AD, and you see that we have AD bar 0. What means? We verify the structure under AD, the structural behavior. But also, what happens after the end of the exceptional actions with the residual strength. Then, after the fire, we have not only to verify what happens after, 60 minutes, but also the second day, the third day, when we reached the cooling of the structure, we returned to the ambient conditions. What is the residual safety of the structure? That means this 0. In seismic combination, we have all the coefficients equal to 1, and in case the sum, the last sum, some variable action is considered, it's affected by psi2 coefficient that is quasi-permanent. Generally, in the highways or waistlines, for instance, we put 0 there. In some code, you may find 0.2, 0.3, or generally 0.2. I already commented this. For fatigue, we have 4 levels of approximation, and we have to certify that the damage is smaller than a limit damage, which is expected by fatigue. The level 1 is a quantitative verification that no variable action is able to produce fatigue. Then there is no need for fatigue verification. that may be verified. Actually, it's impossible. We have some variable action. But we can consider to be in this condition if static actions are repeated less than 10 to 4 times, and for their psi1 is 0, are unable to produce fatigue failure. Then, generally, in this case, it's not necessary fatigue verification. The level 2 corresponds to evaluate a delta sigma due to fatigue that multiplied by gamma ID is 1.1, is safety coefficient for fatigue, is smaller than the limit of fatigue for the delta sigma. Limits are given by the code and are different limits for steel, concrete in compression, and plain concrete. Level 3 approximation, we consider the variable load which is dominant for the fatigue, and we represent this variable load with a single load level Q with an associated number of repetitions during the surface life of the structure. The gamma S fatigue is 1.15, gamma C is 1.5, and then we evaluate for this Q fatigue. You see the formula, the combination formula is similar to the previous one, but we have an additional term, Q fatigue. Q fatigue and the internal action is D1 multiplied by gamma ED. Then all the actions with the gamma equal to 1, but gamma ED multiply all. Gamma ED is 1.1, or for very accurate case, maybe 1. The level 4 is to apply the Miner's rules, then to consider the load history, to build and discretize a spectrum, and to verify the accumulated fatigue due to the spectrum. For the limit state of cracking, already referred Professor Balash, and the same for the deformation. For the vibration, generally we have indirect methods. That is, we limit the deformation, the period of vibration, to avoid the risk of resonance. This is the first approach. Otherwise, we have to perform methods on the structures. With gamma F equal to 1 and gamma M equal to 1, we have the limits, table of the limits in the code. For the combination of actions, we see as a function of the psi parameter that we use, we may define a characteristic, frequent and quasi-permanent, a seismic combination of the actions, and disclose the partial factor method. For the global resistance format, we account for the uncertainties of structural behavior on the level of resistance. The effect of all the uncertainties, material properties, geometrical dimensions, and so on, are integrated in a global design resistance and can be expressed by a global safety factor. The representative values of global resistance and global safety factor are chosen so that reliability requirements expressed in terms of beta are met. The global safety factor, we already said, reflect the variability of structural response due to random properties of basic variables. The limit state function of the structure is described by means of nonlinear analysis, and we have to expect for concrete dominated failure a resistance variability higher than for steel dominated variable. It is clear because we start with the coefficient of variation different for the two materials. The variability of resistance is not constant for a given set of materials and depends on the structural model. But I think you will see in the afternoon application by Dr. Cervenka on this aspect. In practice, the global resistance is expressed by the ultimate F value in this case, then can be resisted by the beam and covers this coefficient, material properties, geometry, reinforcement, boundary conditions, and failure mode. Uncertainties of resistance are described by their PDF, function time, mean, standard deviation, And then we derive the mean characteristic and design resistance of these structures. And the global safety coefficient may be expressed as global safety factor, gamma star R, or as in terms of reliability index also. In the fourth space, RD is then the mean resistance of the structure divided by the global safety factor gamma R star. Gamma R star may be derived by a Monte Carlo simplified approach or may be given in the codes, but we don't have for the moment the values. Gamma R star includes the random uncertainties of model parameters, and we may separate by application of a gamma RD coefficient, which assumes values 1 for no uncertainties, but no uncertainties means exceptional cases when we have a model validation by tests or in the existing structures in which we know very well the structure. 1.26 for model with low uncertainties, but to be numerical validated in any case. 1.1 for models with high uncertainties. These are suggested values for the moment by the model code. The to satisfy approach, and I will finish in some minutes, a general applied for durability is a set of rules for dimensioning for the material and the product selection, and for the execution procedures. This set of rules ensures for a non-violation of relevant limit state during the surface life in the design exposition conditions, of course. The requirements are determined in either two ways, or statistical evaluation of experimental data and field observations, what we are doing starting in this process, or calibration of long-term experience of building tradition, or combining. You see here the durability exposure category are well known, are defined in EN 206, are redefined in new one in the model code and the Euro codes. Design by avoidance consists in avoiding or reducing the detrimental effect sheltering the structure from certain actions like environmental actions, wind also, waves. In Netherlands, you saw the protection by the waves, impact of vehicles or missiles. When we design by avoidance for their durability, we separate environmental actions from the structure with cladding or membranes, we protect, or we use non-reacting materials like stainless steel, alkali non-reactive aggregate, or separate the reactants, keeping the structure under critical degree of moisture for which there is no reaction, or we have to suppress harmful reaction like with the use of electrochemical methods. When we design for seismic action, for the avoidance, we introduce a seismic isolation at certain horizontal level, force level, between superstructures of building and foundation or ground, or bridge deck and top of piers and abutments, or sensitive equipment like containers and supporting structures of foundation. Then we introduce the isolator and practically we cancel the seismic action by the structure. Thank you for the attention. Questions?
Regarding partial factors, the gamma G is 1.35 for the permanent action G, whereas it is 1.0 for pre-stressing action P. So why, just want to clarify myself, why is pre-stressing not taken equal to same as permanent actions or vice versa? Factors, why are they different or so much different?
Yeah. In pre-stressing, we have to distinguish between isostatic and the hyperstatic effect of pre-stressing. For the hyperstatic effect of pre-stressing, what is important, the beam value, because if you have more or less friction, you have a compensation in the different spans. Then it's logical to use the mean value. For this static effect of precistration, there is no difference in the ultimate limit state, because if you start with gamma p equal to 1, if you applied in this section, for some reason, 0.9, you will use of a sigma epsilon diagram of the pre-stressing the 0.1 which is 0.1 which you disregarded, because you recover. You start from a lower point. No? From the point of tensioning, you have a delta sigma available. Then, if you start at 0.9, you have more delta sigma available for the ultimate limit state. Then there is no difference. And this applies in every case, unless there are very, very brittle sections. In fact, in the ENV version of Eurocodes, we introduced these limitations, but were very, very brittle section that is bad design. And in the final version of Eurocodes and the model code has not been introduced to avoid complications which are non-realistic.
Thank you.
Regarding the last highest class, that is in the global approach. So would something like progressive collapse, assessments for progressive collapse due to, like the explosion or the plane that went into the car, would that come under that category?
Yes, but global resistance factor may be used for every case of every combination of the actions. If you refer in particular to accidental actions, you have the procedure is that one. When I design building, for instance, I agree with the owner. I design proposal, but I have to agree because it's a cost sometime. Not often, but sometimes it's a cost. What is the scenario that I have to consider? For instance, I design a building of 300 meters of depth. Shall I consider a terrorist attack with planes? Have I an airport in a certain distance? And around to these buildings, there are buildings of 10 meters or other high buildings which protect him. Maybe a big jet cannot arrive there, or to impact of a certain depth in which may be dangerous, but in the top is not a problem. Maybe that only a small plane will arrive. Then we analyze the situation and we discuss with the owner. Fire, you need fire protection, and at 2 levels. It is important, the global safety factor, for instance, for the event that is at the end of duration of the fire, and for the post-event, because you have an idea of the global resistance. But also this may be contracted with the owner. You may say, I have to give it to you a building which resists 120 minutes to the fire without collapse. What do you want after that? In an high-rise building that we designed together with Professor Corres, we contracted as a bank, with the bank, that with some small modifications, the building after the 120 minutes may be used without practical limitation, because it may be repaired with the people working inside. And this was a requirement of the bank, because there are 3,000 people working inside. We cannot stop the bank. It's the main building of the first or second bank in Italy, then you can imagine. For a terrorist attack with explosions, with explosive, we contracted that a car can enter in the underground with 400 kilos for explosives, maximum. A car, the bearing capacity is that. Then we design all the floors for the underground for this type of explosion. But no bigger truck can enter with tons of explosive. And there are active defense to put this truck at a certain distance, which is, to which is not dangerous for the truck. Then you have to contract and imagine the scenario. When you have finished, you can do what you can imagine, of course. Then you may use for this accidental situation, and in particular for the post-event, the nonlinear analysis, and use very easily the global safety factor.
Thank you.
Okay. Last question.
You mentioned about the model uncertainty, both on the action side as well as on the resistance side. My understanding, please correct me if I'm wrong, that when you talk about the action side, it is the model, that is the structural model that you do. Uncertainty in that is the factor.
In the action side, the models should be cover the way in which we evaluate the actions and the consequence of the action, that is the relation between actions and the effect of the actions. If I have a variable actions, which is, I don't know, the snow, I fix some type of measures. But if I decide other type of measures, I obtain a little bit different values. Generally, I don't know, for traffic or wind, for instance, I measure for several hours. Then I divide the interval in elementary steps, which are in relation to the variability of wind, of course. Then I take the maximum on each interval, and I build the PDF of the maxima. And on this PDF of the maxima, I assume a characteristic value, a fractile. But if we change the interval, we have different evaluation. Then I cover the errors, the uncertainties in the evaluation of the actions. And then a second step, knowing the actions, there is in the middle the structure, I cover also the uncertainties in the evaluation of the structural response when subjected to these actions.
And what about the model uncertainty in the resistance side?
In the resistance side, I have to cover the uncertainties between the resistance on site and inside the structure, and the measure of the resistance itself. For instance, if I test the concrete with cube, which is common, or cylinder, I have some resistance. But if I drill a core in the structure, I am not to expect to have the same resistance. Generally, 15% reduction is accepted, except the effect of drilling, which is not considered within 0.85. Then I have to cover these uncertainties that I have on the material and the use of material inside the structure. If I have massive concrete, is different if I have low hardening of high hardening cement. Very different the effect. If the production of heating during the hardening is high, I have a damagement of concrete. Generally, we put the limit which are referred to chemical aspect. It is, a classical limit is 80, 82, 83 degrees to avoid the delayed formation of a trangite. This is a problem of delayed cracks, but you have damaged also the concrete because due to the thermal effects, generally you have micro cracking for non-uniform diffusion of increasing of temperature and reduction in particular of temperature. You have a micro cracking which reduces the behavior of concrete, the elastic modulus, and also the resistance.
Sir, one question. On the action side, on the action side, we are talking about the material properties, etc. But what happens when the loading is not with a single mode, but it's a bimodal distribution? I mean, take an example of traffic load, and certain bridges being constructed in the part of the country where we don't expect heavy industrial vehicles moving. And dominant vehicles are of a smaller magnitude, maybe almost a single model. As it happens in India now, more and more roads or places are giving an access to the heavy loads coming all across the country. And now suddenly the value of the loads have shot up. If you see the local distribution, it's bimodal. It's not a single model.
Yeah.
Now, how do the partial factor method can be applied when there is a bimodal change, and especially when it is likely to change over the period of time?
Yeah. It's not a problem of partial factor. This is a problem of definition of actions. The live loads on bridges has been calibrated after years of measures in two particular sites in the Central Europe in which there is a lot of traffic. One is in France, one near Netherlands and Belgium and Germany. Very, very heavy. And of course, they have been interpreted so that you design today, but you design for a structure which should remain on the life for 100 years. Then you cover the future. Not to say if you have a different particular situation. What happened in Netherlands, before to start to repair bridges, they measured the traffic. They did measures for 2 periods of 6 months near, in a highway near the Rotterdam harbor with a lot of traffic. I know the history because my PhD student has been sent by to the professor Ravenvelder to elaborate these measures. And he discovered that there are trucks of 100 tons traveling on the way, which is not permitted, but there are. But at the end, then they are dangerous not for the full structures, but for the local effects. At the end of elaboration of what happened, that this heavy traffic on isostatic structures was 5–6% less heavy than the application of Eurocodes on the isostatic, but was of about 20% less heavy, less onerous for the hyperstatic structures, because the Eurocode don't take into account the reduced probability that when you have a continuous beam, all the regions interested in the influence line are affected by the maximum load. This is a probability which requires a coefficient smaller than 1. If you use the traffic load, you put 1, 1, 1, 1, and 1. Then with this approach, they saved a lot of bridges by repair intervention. Maybe you have a particular infrastructure which is subjected to reduced traffic for socio-economical conditions, because you are sure that in the next 50 years, this region will be not developed. And you measure the traffic and you apply your traffic in the design, in agreement with the authorities, of course.
Oh, thank you very much for your very